In this lesson, we are going to define the purpose of the vertical speed indicator, or VSI, and consider how the VSI works. We will also look at the types of VSI presentation and the errors the VSI is susceptible to. To conclude, we will look at the instantaneous vertical speed indicator, or IVSI, and a simple way to calculate a rate of descent. Let us look first then at the purpose of the VSI. Here, we can see an example of a typical VSI from a light aircraft. The VSI indicates the rate at which the aircraft is climbing or descending by sensing the rate of change of static pressure. It will also indicate level flight when zero climb or descent is shown. Rates of climb or descent are usually indicated on the instrument dial in feet per minute, although meters per second may occasionally be used. So how does the VSI work? The VSI may be thought of as an airtight instrument case, with a pressure sensing capsule and a metering unit inside. Both the pressure sensing capsule and the metering unit are fed with static air. Inside the metering unit is a restrictive choke, and the purpose of the choke is to slow down the rate at which static pressure can change within the airtight instrument case. In level flight, the static air pressures on each side of the choke will be equal. However, the static pressure will change as altitude changes. Any change will be sensed immediately by the capsule, but the static pressure change in the instrument case will be much slower because of the restrictive choke. This causes a pressure differential, which will be maintained while the aircraft is climbing or descending. Also, the rate at which the altitude is changing will be reflected by the size of the pressure differential. Once the aircraft is in level flight, the pressures will equalize after a few seconds, and the VSI reading will return to zero. Click Climb or Descend with the mouse to see the principle in operation. As we have seen, the VSI uses the rate of change of static pressure to indicate a rate of climb or descent. To be of value, the indicated rate of climb or descent on the VSI must remain consistent, regardless of altitude and temperature. However, the higher the altitude, the less dense the air will be, and the slower the rate of static pressure change will be for a given change in altitude. The metering unit self-compensates for these changes. To achieve this, static pressure is directed through a capillary tube and an orifice in the restrictive choke of the metering unit. The effects of the static pressure in both these components combine to self-compensate for pressure variations with altitude and temperature, thereby giving a near consistent indication of rate of climb or descent, whatever the altitude or temperature. The VSI is susceptible to the following errors. The first error to consider is instrument error. This results from manufacturing imperfections, friction and wear in the mechanical linkages. Next is position error, which is sometimes referred to as pressure error. As we have seen, the VSI relies on static pressure for its operation. The static source may be subject to position error, which occurs as a result of suction and turbulent airflow around the static source. The VSI may therefore incorrectly register a rate of climb or descent, particularly when the speed of the aircraft suddenly changes. This error may be noticeable on acceleration during the takeoff ground roll. The third error to consider is maneuver-induced error. Again, this error is related to the source of the static pressure. Short-term fluctuations in pressure at the static source during attitude changes, especially during changes in pitch, will cause the VSI to indicate a false reading. This error is especially noticeable during pitch changes, which occur with flaps and landing gear operation. The final error to consider is time lag. If we think about how the VSI operates, it can be seen that it will take a few seconds for the pressure differential to become established in the climb or descent. There will also be a time lag on levelling out, while the pressures in the capsule in the instrument case equalize. This error is most noticeable after a prolonged climb or descent, especially at a high rate. Instrument, position, maneuver-induced, and time lag errors are all to be expected in a normally functioning VSI. When considering the VSI, however, a blockage or leak constitutes a malfunction and should be viewed as such. A blockage in the static source will result in the VSI ceasing to function. If the blockage occurs during a climb or descent, the VSI indication will gradually return to zero as the differential pressure equalizes. If the blockage occurs in level flight, the VSI will read zero during a subsequent climb or descent. If the static line to the VSI should fracture within the pressure hull of a pressurized aircraft, the static pressure sensed will be the cabin altitude pressure, and the VSI will only sense a pressure change when cabin altitude pressure changes. The VSI will continue to function if leakage occurs outside the pressure hull, because differential pressure can still be established in a climb or descent. Pressure fluctuations in the static line may result in transient pressure errors, but the effect will be small. There are two basic types of display for the instrument dial. The display on the left uses a linear scale to show the rate of climb or descent. In this particular example, the display is graduated in equal increments of 1,000 feet, up to a maximum rate of climb or descent of 5,000 feet per minute. In the example, the VSI is showing a rate of descent of 250 feet per minute. The display on the right shows the same information and displays a rate of climb or descent of up to 4,000 feet per minute using a logarithmic scale. As we can see, the increased sensitivity of the logarithmic scale at the lower rates of climb or descent makes the logarithmic display easy to read where accuracy is required. As we have seen, a shortcoming with the VSI was time lag. This problem is overcome by the instantaneous vertical speed indicator, or IVSI. The IVSI is similar to the VSI, but incorporates a vertical acceleration pump, or dashpot, in the static pressure line which serves the capsule. We can see the principle illustrated in diagrammatic form here. Inside the dashpot is a piston, which is centered by springs. As a climb or descent is initiated, the inertia acting on the piston in the dashpot displaces the piston, causing an immediate differential pressure. Once the climb or descent is established, the piston is slowly recentered by the dashpot springs, and the pressure differential is maintained by the metering unit. We can see here how the dashpot works in the climb. The piston in the dashpot immediately falls and decreases the pressure in the capsule. The capsule contracts, and the pointer on the IVSI dial will give an instant indication of a climb. In the descent, the piston in the dashpot immediately rises and increases the pressure in the capsule. The capsule expands, and the pointer will give an instant indication of descent. The final point to note on the IVSI is that as the dashpot senses vertical acceleration, turbulent flying conditions and bank turns can give false IVSI indications. For example, in a steep level turn, the IVSI will show a false rate of climb. To conclude this lesson on the VSI, we will take a look at how a rate of descent can be quickly and simply calculated using the 1 in 60 rule. The 1 in 60 rule states that if the range is 60 units long, then the height will be the same number of units as the angle in degrees. For example, If the glide slope angle is 3 degrees, the height will be 3 units. If the range is therefore 6,000 feet, the height will be 300 feet. 6,000 feet is a reasonable approximation of a nautical mile. Therefore, on a 3-degree glide slope, the height loss required will be 300 feet per nautical mile. An aircraft with a ground speed of 60 knots will take 1 minute to travel 1 nautical mile. Therefore, the required rate of descent to be indicated on the VSI will be 300 feet per minute. A simple formula to remember is, for a 3-degree glide slope, the required rate of descent in feet per minute equals 5 times the ground speed in knots.